Hello and welcome to the fifth in my series of videos, all under the title of absolute relativity. And as I said before, the reason I've called them that will become more and more obvious as we go through. But they're all designed to dispel the mysteries and the fairy tale physics involved in quantum physics, quantum mechanics, nuclear physics, and so on. Doing this by the by a new description, using the simple realization that photons and electrons, and effectively all subatomic particles, do not have independent existence. They are all descriptions of the energy levels and the energy exchanges between atoms, between matter. And this is a simple but radical realization. If you've watched the previous 4 videos, you'll see how very easily this description overcomes a lot of the... It provides a description, a comprehensive description of what's happening at a subatomic level. As I say, this is the 5th in the series. We started off with Young's double slit experiment and then did quantum entanglement. And if you look at that one in quantum entanglement, there's so much written, so many experiments done on quantum entanglement to ensure, yes, this entanglement is real, but how does it happen? And all sorts of fairy tale ideas get attached to it. Well, if you look at my description using this absolute relativity, using the idea that photons and electrons do not have independent existence, you see it's so simple. The answer to it is so simple. But that was the second, quantum entanglement. The third was the photoelectric effect, and then we discussed the nature of photons and electrons, and the fact that we don't need them to describe what is happening at an subatomic level, that it's all done in terms of protons and neutrons. And the neutron is just a proton at a different energy, slight different energy. As we said in the last one, if you can get a neutron, a free neutron, it lasts for about 14 minutes, I think. Its half-life is about 14 minutes, at which time it exchanges some energy with some other particle and then reverts back to being a proton. So all we have is protons. And if you look at the periodic table, you can see this. Every time you add a proton, you get a new element. The periodic table would say you add an electron as well, but the electron is just the proton. It's the energy level of the proton. Now, what I was going to do in this video, it was going to be just about quantization. Now I decided, when I was thinking about it, I think I needed to incorporate spin. So this one is spin and quantization, and we're going to cover spin first. And to do that, we're going to be looking at this neon atom that you see on the screen there, neon atom, with the conventional, in its conventional description, you have the protons and neutrons sitting there at the nucleus, and the 10 10 electrons in orbits or orbitals. Now these two, first of all, at one energy level. We're going to be talking about these energy levels when we do quantization. These energy levels, or shell, and these 8 in the next energy level or shell. And but what I say is, this is a pretty good description of the neon atom, but at the nucleus here we have the neutrons, around which orbit the protons. These are the 2 protons, 8 protons at these different energy levels orbiting their mother, their stabilizing neutrons. And don't forget, each one of these protons has its own energy level, which is depicted here. But when we're measuring this, we're measuring from somewhere out here, and you will see we're measuring sort of from what would be its ionization level. We're not getting any closer than that, and we're measuring here, but we may measure it in so there's its sphere of influence. We may measure it here, we may measure it here, we may measure it here, and don't forget it's in orbit around here, so it could be anywhere in there. We could make contact with it anywhere in there, and that's how you get the probability of finding it in a particular place. And so, as I say, we will cover the energy levels later on, but first of all, spin. Now, according to convention, the protons and the electrons have the same spin, and that's a half or minus a half. Why would the electron have the same spin as the proton? Because it is the proton. There it is. You can get a situation where you say it's possible that you can get the electron to have spin minus a half and the proton to have spin a half. And I'd say no, it isn't that. The proton here has spin a half. Where you're measuring from, your measuring instrument, the atom here, has minus a half. That's all relative to the measurement. It's not a, and that can make a difference to the energy that you measure, of course. There it is. So each of these has spin of a half or minus a half. Now, before I go on to say to describe that anymore, you will read in different places that spin cannot be described in physical or classical terms. Spin shouldn't be understood as the rotating internal mass. Spin is a quantized wave property. Yes, but it is. But I'd still like to see if I can make a rotating mass description of spin that makes sense in terms of a wave property. Let's have a look at that. Let me take this one out, bring this one in. I've marked this one up with these. This is to say the wavelength, the frequency of this proton is here, and that is one wavelength. It's at a particular energy level according to where it is in the shells, and more energetic it would be, the more, we go from blue to red and so on. So there it is. That's the energy of it. It doesn't, the energy, we're not concerned with the energy, the actual energy levels right at this moment. Sorry about that. None of this is scripted as such, so, and we'll always get some cock up along the way, which I'm not worried about. We'll always get there. So this is the energy of each of these protons, and this proton is in orbit around here, and this one is with it in its orbit. All these orbits around the neutrons in the nucleus. Now, that's not what I meant at all. There. All these, sorry about that. All these protons in their orbits. Now, let's say this one is at half. If you look at this one at this angle here to this one at this angle here, and so on as we go around. Now, if we look at this here, this goes, this one goes, it's actually in opposition. So if this one is a half, this one is minus a half. And there it is. That's what these spins are. And if we carry on with this and still call this a half, let's still call this one a half. It doesn't make any difference. This one's minus a half. This one's minus a half. So every time the opposite, we have a half and minus a half. Half and minus a half. And back to a half again. So every time the opposite one has the opposite spin, just because it is opposite, and its spin then is in opposition. Half and minus a half. you can get more complex atoms when you look at their overall spin. You kind of add the spins up. So if we add all these spins up, the overall spin, because you've got halves and minus a half, is 0. But if we had an atom with, then the next atom up would have another, if we add another proton to this and get the next element, that would be at a half or minus a half. So there's going to be a overall, the atom has that, and if we add another proton, this can be at a half or minus a half. Now, if it's in opposition, which it probably would be, it would be over here, it would be minus a half. But under certain circumstances, we could get it to be a half and a half, and so we'd have a overall spin of 1, a half and a half. That's how this happens, and so we end up with this, what we call a singlet state, where it can be in one condition, a half and minus a half, but if we have the two of them and they're not necessarily paired, we have what you have, if you look all this up, it could be what's called a triplet state. This doesn't make any difference to what I'm saying about electrons having no independent existence. This triplet states and everything, a triplet state means they could be both aligned, opposite, or aligned in that direction. This is a triplet state. Now, it doesn't make any difference. So the triplet state, all of this triplet state conventionally is applied to electrons. So I say, well, exactly the same thing applies here to protons. It doesn't make any difference. There it is. You just don't have you don't need the electron to make these descriptions, and you can get such things as spin 3/2. Something that has a spin 3/2, which is you can create this from an alloy of yttrium, platinum and bismuth, and they form so-called Cooper pairs of electrons. When you core this thing, it becomes a superconductor, so it has no resistance, so you can set it off in a ring with a current flowing, and the current will flow forever, provided you keep it supercooled. But this superconductor, this is a very complex alloy, yttrium, platinum and bismuth, and creating these so-called Cooper pairs. And what I intend to do in a much later video, probably as an addendum video to this series, is to have a look at these Cooper pairs and make an explanation of what's happening using this description. So there we have the description of the wave property, the way the wave property is changing according to its position with respect to its opposite to its opposite proton. That is spin of protons, so-called spin of electrons, which is just as described the spin of the protons. Now, if we're going to look at a spin of protons here, the wave function is a half or minus a half. You look at all the calculations you have still apply, but this just makes a neater description, just describes what's actually happening. And also then, if we look at photon polarization, if this atom here, if this proton here is sent out to this energy level and then exchanges this amount of energy with a receiving atom outside, this is how the wave function is polarized. If we energized this one and from the same place received this amount of energy, the wave function is polarized in that direction. So it's gone from let's label this, I want to keep that. Let's label this for polarization 1, minus 1. This is the same polarization here, don't forget, minus 1, 1. And we can still call that 1, and that 1, minus 1, and that 1, minus 1. So get 1, 1, minus 1, minus 1, 1, 1, minus 1, minus 1. There it is. There is spin of the proton. There is spin of the photon, which is the polarization of the proton. As simple as that. And let me leave that's it. Okay, so wrong way around. There we go. So spin of a half and minus a half for protons, for conventionally for the electron and a proton. There it is. There's your spin of half and minus a half, and for the photon, spin of 1 and minus 1 according to its polarization. simplified the whole thing. But have a look at this. This I've taken from the spiral structure of electromagnetic waves and of stationary electromagnetic fields by Solomon I. Khmelnik. I hope that's correct pronunciation. I apologise if it isn't. But in this paper, you can see this paper here. If you want to take a note of that, you can look up this paper. This is based on the new solution of Maxwell's equations. The spiral structure of electromagnetic waves and stationary electromagnetic fields was theoretically predicted and experimentally confirmed, and it was also shown that spiral structures so exist in all waves and technical devices without exception. Spiral structure of electromagnetic waves. I want to have a bit of a look at that. Let me take that out. And there you see the electromagnetic waves. And as we are direction of propagation, the electromagnetic waves, there are the electric field, there's the magnetic field at 90 degrees at 90 degrees to each other. Now come back to this description. And back to that. Just supposing we take any of these protons and say, okay, this diagram, all these protons, let's say this is a lithium atom. So we'll have these two here, and then a single one in the next, a single proton in the next energy shell. Now, let's say that's its orbit. So now you see its electromagnetic wave. Here, here, here. What's happening is that it's spiraling. If you were to plot that wave, you would have this wave turning over, so that when we went from there to there, around there, this would lay down, this would stick up, so your electric field would be here. So you're actually moving along the propagation, so that the electric field would be laying there, the magnetic field would be up there, so on. Next 90 degrees, then your electric field will be down there, and your magnetic field will be laying behind. So in effect, what you'd have is this whole thing spiraling along as we go. I hope I've been able to make that clear, but that spiral effect, then, if I bring it back to here. Let's take that one out. Bring that back to here. Then you see this electromagnetic wave spiraling, and that's what it's doing. That beautiful. So there it is spiraling. So this is one single proton now in its orbit, and its electromagnetic wave is spiraling around there. Of course, it has to. It couldn't do anything but. So, that's it. That's covered. That's covered spin. So now I'm going to go on to talk about quantization. So we'll be referring back to spin as we go, but you can see now spin is a wave property, but you can describe that wave property in terms of rotating internal mass. Right, don't go away. I will be back soon, and we're going on to talk about quantization. And so on to quantization, and in this, mostly everything that we're talking about in quantization is exactly as you would read anywhere, but instead of electrons shifting round in shells, we have protons. So I'll start back at the proton itself, the bare proton, and in its conventional drawing we have the proton and the electron in orbit around it, which is an orbit, not an orbital. We'll have a look at the difference between them in a little while. And your proton sits there at is measured at minus 13.6 electron volts, but as we said before, you're measuring it from your datum point into here. That's minus 13.6 electron volts, and essentially that 13.6 electron volts is the energy at which you'd have to give the proton for it to reach its ionization level, which is its boundary, its ability then to transfer energy to the outside medium, whatever that happens to be. So there's our proton, and the shell is the energy level that is read. It could be read here, it could be read here. This is, ignore this. This is the boundary of it. It could be read in any of these places. You could find So make your reading in any of these places, and classically in the accepted science, that is locating the electron. Well, it is. It's just reading the energy of the proton. You read it from anywhere within its energy boundary, because the proton doesn't actually have a boundary. It just spreads out as it goes. Its energy spreads out as it goes across a sphere. We're always talking about spheres, don't forget. So it spreads out. I'm just going to get rid of most of these 30 marks, but that'll do. Now, if we then add another proton, and now we've got to add electrons to, another proton. Here are your positive protons. This, in conventional Bohr diagram, is the diagram. Now we've got two neutrons binding the whole thing together, and I would say, no, what you got now is the two neutrons in the nucleus, and orbiting them are the two protons. They're in orbit around this energy. So while we have this energy level at minus 13.6 electron volts, there it is. These is saying that this orbital is at that level, but what's at that level of the energy level are the two protons that are circulating it. And as we saw before, one will be in half a wavelength out of phase with the other. So we have one at a half, one at minus a half. That's the spin difference. And the spin difference is just that if we took this all the way around and took that wavelength there and that wavelength there, they would be out of phase with each other. That's all that's happening. These two are circulating, orbiting around this center. Then let's go on straight away. I won't bother cleaning that up now. Let's go on straight away and add already got some marks on this one. It doesn't matter. I'll add another proton and neutron, and here we have the same two protons in this, at this energy level or shell. This shell is n equals 1, and these protons are at 13.6 electron volts. Now it means that this shell, this first shell, N1, or there is they are lettered as well. They go K, L, M, or K. We'll have a look at that. But n equals 1. It's so much easier to say N1 because of what we'll see in a second. This electron depicted, this electron, this proton here. Now what's happened is this sphere here has, let's say, doubled its size to here. Now when n equals 1, now this proton is spread out across a bigger sphere. And so that what we have, the energy that this is sitting at, is 13.6 electron volts divided by n squared. This was divided by n squared, but n equals 1 here. N equals 2 on this second level, so that this equals 3.4 electron volts. And as we saw before, if we get this, it probably wouldn't happen with this, but just with this particular atom, but just for the sake of description, if we can get this proton to move out to here by energizing it, it will take that energy and shift out to here. These are all negative, by the way. Don't forget they're negative. So that this is more positive. So it's increased. And then it will dive back, and in diving back, that is what we see. In diving back, because it gives up its extra energy to a receiving atom. Nothing happens until then. It will just stay at this more excited level. But as soon as it does, it gives that up and jumps back there. So this is instantaneous, whereas if we give this 3.4 electron volts, it gets to the edge where of its boundary, where it can transfer energy across a short time to the medium that it sits at. I've just gone over the photons and electrons again, but there we have these two shells, M1 and N2, or K and L. They go K, L, M, N. You know, 1, 2, 3, 4. These two electrons, sorry, these two protons sitting here are -1/2 and 1/2 spin. So they are, as we saw just now, they are in opposition to each other. They are that much out of phase. This one on its own, we don't have to worry about, you know, this atom is at this energy, but this is the only proton in this shell, so it doesn't matter what its spin is or anything, it's fine. We can't have another one of the same spin and all of the same attributes, because all those attributes are taken up, and that is the exclusion principle. We can't have two being the same. You can't have two here being both half spin. You can't have these two being half spin, because this one's already at that, and this one can't be at that because that's already taken up around here. It's got to be opposite, and these will be the same. And in effect, what I'm going to show is all of this information is just the same as applied to the conventional electron model, but now using it as the proton orbit and orbital model, then it starts to make sense. Let's move on to take that one out. Now we move on to neon, because we've added, or nature has added, and every time we add a proton and neutron, we get a new element. And so we've gone from the 2 in the first shell to having just 1 in the second shell. We've gone from the 2 of helium to the 3 of lithium, and now we've kept going through the elements and added all of these protons and the corresponding neutrons, which will be in the nucleus. And now we're going to see each of these is 13.6 eV divided by 4. So they're all at, sorry, that's negative, minus 3.4 eV. All of them. And let's say this one's lined up with this, so we'll call this spin half. It doesn't matter if you call it spin half or minus half. It's just a label. These things are just labels. We'll go on to see more labels in a minute. They don't have values, they're just labels. But let's stay with that a second. So these are all half. That's a half spin. That's a half spin. That's a half spin. Now, look at that. It's minus a half spin. So that one's minus a half. Opposite. The one opposite this one is minus a half, and so on. And every time we look at the opposites, we get half, minus a half. Because now if we look at this, and look, add these up. The minus 3.4s. We've got, because we divided them by 4, now what it lets us do is to put 1, 2, 3, 4 at 1/2, at half spin, 1, 2, 3, 4 at minus half spin, which was 1 half spin in the first shell, 1 at half spin, 1 at minus half spin. Now we've got 4 at half spin and 4 at minus half spin. So of course we divided the 13.6 by 4. Now we've got 4 of them. We've gone back to our 13.6 and 13.6. And if we looked at this, then we've gone back to, and if you were to look at these waveforms, this waveform at this point would be half a half wavelength out of phase with this one. That's what it is. We've gone back to a full shell. I think we will find because it's full, it doesn't want to react to anything else. And I think we find that, like helium, neon is a noble, will be a noble gas. But there we have it. That's the next shell out, and all that's happening is the energy is spreading out. Because it's spreading out. Now look, if I put the next one in, n equals 3, what we would have is minus 13.6 eV divided by n squared, 9, equals, what does that equal? I don't know. Where's it gone? It doesn't really matter. 13.6 divided by 9. 1 minus 1.51 electron volts. So all that's happening is, as we're coming out to here, we're getting, it gets easier and easier to energize this proton to its ionization level. We'd only need to give it we give it 1.51 electron volts to ionize it, to allow this proton to communicate, to transfer directly to the outside world. And again, if we jump a proton energy from here out to this level, it will sit at this level, transfer that energy to a receiving atom and fall back instantaneously as a photon. And the photon energy would be at a 3.4 volts minus the difference between these two, 3.4 and 1.51. That would be your photon energy. None of this is really any different, but just this idea, it simplifies what we're looking at. That the explanation of these things revolving around the nucleus and what the nucleus is. This makes sense if we make the nucleus your absorbed protons, your neutrons, and they are orbited by these energetic protons. Okay, let me take that one out and start that again. Now, this exclusion principle thing, it means that each of these energy levels, if this is at a half spin, this energy level is taken up now by this one at half spin. All it can have is, because we're at minus 13.6 electron volts, all it can have is another one at minus a half. It's opposite 2. Now this one, we're always confined to this 13.6. This whole structure is built on the ground level energy of the proton, 13.6. Always 13.6. Now, to make up 13.6, we can have these 4. Now the thing is, these two in N1 are revolving around in opposition to each other, revolving around the nucleus. These two are effectively in phase with them. Effectively in phase with them. And this lot are revolving out of phase with this, which means, although I said all this adds up to minus 13.6 eV, it does almost, but not quite. These, because they're revolving out of phase with this, there's a bit of extra energy to them, and you get what is called a subshell. It's still N1, all this is N1, but now we have the subshells, and they also are labelled by letters. We have S, P. So if I were to draw this, oops, I didn't mean to do that. Take it out of that one. And then I'm going to put, I'm going to have this now. Okay, sorry about that. Now, there's our nucleus with our neutrons. Here is N1 with the 2 protons. Here is N2 with the 2 protons aligned with these. Now the rest of them, they are running, so we've got another 3 on each side. Now because they are out of phase, they're running with this little bit of energy, and they are actually running on this subshell, which contains these 3, and these 3 will be out here on this subshell. And labelled. So N equals 2 has 2 subshells, and they are labelled S and P. It's still the one shell, N equals 2. We don't have any subshells on this first one, and none of this is any different from if you were, looking at it in the old electron one. But as I said before, it makes sense now when we look at this in revolving protons here in this subshell. So we have N equals 2. There is I'm just going to say this is a label for the minute. L. You can look up what the definition of this is, but let me say, as far as my explanation is concerned, all I have to say is L is a label, and L equals N minus 1. For this shell, N equals 2, L equals N minus 1, L equals 1. Now what we have in this N2, we have magnetic spin and magnetic moment. That is, moment gives it this further out, slightly further out orbit, slightly more energetic orbit than the S. So ML equals L if L equals 1, ML equals minus 1, 0, 1. If L, for the next one out, N equals 3, L equals 2, ML equals minus 2, minus 1, 0, 1, 2. So we'd have 5. And you'll see how this fits here into this explanation. And all the time we have ms, which is the magnetic spin, is a half or minus a half. Ms is the magnetic spin of the particles, not of the atom itself. The atom itself is made up of the spins of everything that's in it, but each time ms is the spin of each particle, each proton. So that when we have this shell, we say that one's full up by these two. This outer shell, this first part, the S, the first subshell of n equals 2, is filled up with the first two in line with those on the on N1. From there, because we are spinning with them, we are also spinning in a different direction here, which gives it more energy. So then we have n equals 2 for all of these around here, but now for these 6 we have call these 3 here spin half. This one is at ml equals 1, this one is at ml equals 0, this one is at ml equals 1. So that in this subshell the energy levels are all taken up, and this side would be the same except for the spin would be minus a half. And that's how the exclusion principle works. It is just, this is where this explanation using protons comes into its own. It's just positioning with respect to this, say, axis. This is our axis. The first two are spinning with the axis. The only two on the inner one are spinning with the axis. The next two spin in line with the inner axis. These do not. They are spread out. They are circulating, orbiting in orbitals. These two, these are in orbits, straight orbits around the center. These are in orbitals. I'm going to have a look at orbits and orbitals in a minute. But just take that then, that when we go into the next shell, n equals 3, first of all, it would have an S subshell with its 2 interlined, and then it would have a next subshell with these 3 in a line, and then it would have a next subshell with the rest of the atoms, the rest of the protons that are allowed to fill up that total shell in total, all at, what was that, minus 1.51 electron volts. And you'd find then in this next shell, if you took all the subshells, the 3 subshells, everything in it, added them up, ignoring the differences, the slight differences in the orbitals, then you'd get back to your minus 13.6 electron volts every time. That's the same. So let me lose that, bring us back to one of these, and here we have this is on the in orbit here. These are in orbit with them. These are in orbits this way. Now, if we look at the orbit, the axial orbit is doing that. This orbit here is starting off on this orbit, but this is turning it around. Don't forget, this is spinning here while this is coming this way. So in effect, with that respect, the orbital is doing this. So the ones in the protons in the S are just doing orbits. The protons in the other subshells are being turned by the S orbit into this shape. As it's coming, this is turning over. If you can envisage this turning over, as this comes around, it turns over, and effectively, when you're looking at it, the orbital ends up as that shape. So there's an orbit, there's an orbital. The ones in the S sub shell are in orbit. In all of the other subshells, however many you may have, they're all in these orbitals, which are shaped by the orbits of the S subshells, shaped by the orbits of the axial S subshells. That, let me bring this down to just make the point here. Sorry, I just want to hide that. Make the point here. This is a diagram. As we go out, I hope you can see that n equals 1, 2, 3, 4, K, L, M, N. And so always for n equals 1, there are your two electrons. I would say are two protons. Every time it says electrons, let's read protons. Electrons, we read protons. We read protons. There they are. This is so essentially it's no different. So in n equals 2, you're going to have these two subshells, and there's your 2 axial and the 3 sets running round out of phase. It kind of shows that in phase, but we've seen they're out of phase with that and given the orbital shape. The next one, n equals 3, or the M shell. There's your 2. There's your first 2. There's your next shell with 3 lots of 2, and then you'll get 5 lots of 2 in the M shell, all in orbitals, all shaped by the axial S, the first shell, and so on. You see, none of this diagram is showing that with electrons, and I say no, take the electrons out, put protons in there, and it makes sense. The orbits and the orbitals make sense. Here's a diagram of the orbitals. They're the subshells. Let's say this is N2, N equals 2, and we have those in the 2s in the S shell in an orbital, and the other 3 in the P shell, the next shell out, are given this shape by the orbit of this. This is running here, so it runs like that. Given this shape, it's just an orbit for this, but it's given this shape by the orbit of the axis of the atom. And then this one would be here, here, and then here. That's how that would look. And these are diagrams of the movement of protons. And just bring that back to there. I like to leave it on a clean image because we kind of got to the end. Now, shells, subshells, and so on. It all makes sense when viewed as protons in orbits and orbitals around the neutrons, the nucleus of neutrons. But a full understanding of the way the shells and subshells, I hope that's a full enough understanding of the way the shells and subshell works. We have shown that there's no need. What we've done in this, I mean, you can read up more about shells and subshells, and in the literature it will always be talking about electrons, but what we've shown is there's no need to include the electron, no need to include the electron in any explanation of subatomic processes. We've already established in previous videos that the electron and the photon have no independent existence. Indeed, they should be regarded, if regarded at all, as a means by which to describe the energy of the proton and the atom as a whole. And again, indeed, the proton should be regarded as the fundamental particle from which everything in the universe is constructed, as can be seen quite plainly in the periodic table. Anyway, that's as far as we're going in this video. So far we've established that the electron, the photon and the Higgs boson are all unnecessary, misconstrued particles. From here we shall show that all subatomic particles should be viewed as similarly misconstrued energy exchanges between protons with no independent existence. So I hope you will join me in the next video, which will be about the Schrödinger equation and the measurement problem. Hope I'll see you there. Bye bye.